Hello, we are Group 32, and our project is 2HADRAD, a portable life detection radar. 2HADRAD is a handheld system designed to assist search and rescue teams by detecting human presence and estimating the location of individuals in real time. The device identifies indicators of life such as movement, breathing, and body heat using multiple sensing technologies. When these indicators are detected, the system generates visual alerts and positional information, helping responders identify potential human presence and making faster decisions in low visibility environments. This slide shows the core hardware architecture of our system. The sensor subsystem, highlighted in yellow, contains the sensors used to detect indicators of human presence within the device's field of view. At the center of the subsystem is the ESP32 microcontroller, which serves as the main processing unit. The ESP32 collects data from the sensors, manages communication between subsystems, and performs the real-time processing required for the device. The system integrates several sensing technologies, including an infrared thermal sensor, which detects body heat and temperature differences in the environment, an ultra-wideband or UWB module, providing distance measurements that help estimate the relative position of detecting objects when indoors. The system also includes an inertial navigation system, which provides orientation and positioning data. This subsystem integrates an IMU for roll pitch yaw measurements, a barometric sensor for altitude estimation, and GNSS GPS for global positioning information. Finally, an ultrasonic sensor, or USS, is used as a proximity sensor to detect objects that are very close to the device and act as a safety mechanism for the radar. The data from these sensors is transmitted to the ESP32, where it is processed and used to generate information to display to the user.
The sensing component of our system is a 60 gigahertz millimeter wave radar based on the Texas Instruments IWR6843 AOP EVM module. The radar transmits frequency modulated chirp signals and measures the reflections from objects in front of the device. Using onboard digital signal processing, the module analyzes those reflections to detect motion and very small chest displacements caused by breathing and heartbeats. The radar module is powered by a regulated 5-volt line from our power supply board and shares a common ground with the rest of the system. Communication with the ESP32 occurs through UART connections routed through the radar's 60-pin connector. Two UART interfaces are used, a configuration UART, which uses TX and RX lines so that the ESP32 can send configuration commands to the radar firmware, and a separate UART data interface that continuously streams the radar's processed measurement data. The radar firmware packages this processed information into structured binary TLV packets, which are transmitted to the ESP32 through the UART data stream. The ESP32 parses these packets and extracts the parameters we want to display. In our current implementation, the LCD shows heart rate and breathing rate, but the firmware can also output additional information such as target range, motion detection, signal quality metrics, and point cloud detection data, depending on the configuration. In this architecture, the radar performs the sensing and primary signal processing, while the ESP32 handles configuration, packet parsing, and presenting the results to the user through the display.
The user interface subsystem can be seen below in pink. Everything on this PCB is powered by the 3.3 volt rail. First up, we have the red LED, which we have programmed to turn on every time the radar is active to alert the user to stay away from the radar at least 20 to 30 centimeters. Then we designed an audio amplifier. This will alert the user whenever the power system is running and also when a human is detected, and we will probably add some more audio alerts in there. Then we have the LCD, which is the main component of the user interface system. It shows the heat map, the map of the location of the victim, and it also displays a screensaver whenever the system is idle. And then we also designed a 5-way navigational button on this PCB to allow the user to navigate the screen without touching it for environments where it might be wet or the gloves are too heavy. And everything on this board connects to Shannon's board with the ESP32 through screw terminals.
The UWB code resets and initializes the DWM3000 anchor ranging hardware that's on the sensor subsystem PCB board, periodically pulls it for new measurements, and uses the resulting value as live distance from the main unit to the remote tag unit. It rejects clearly invalid ranges and stores the latest good tag distance with a timestamp, and then fuses that UWB tag to main distance with the INS derived distance from the chosen start point, weighing the two based on how closely they agree and smoothing the results so the displayed range is more stable than either source alone. The INS code calibrates accelerometer and gyroscope bias, updates device orientation with the Magic filter, rotates measured acceleration into east and north navigation accesses, and applies several corrections to control drift, low-pass filtering on horizontal acceleration, deadbanding very small acceleration values, damping integrated velocity over time, and clamping maximum velocity. When GPS is valid, it resets the local position to GPS-derived coordinates. Otherwise, it continues dead reckoning and logs the user path and marked victim locations relative to the selected origin. The later thermal rendering block, starting around line 985 here, handles the live thermal screen itself. It throttles updates, retries the MLX 90640 IR frame reads, and smooths successive temperature frames, upsamples the sensor image from 32 by 24 to 64 by 48, converts temperatures into RGB colors for TFT, and only redraws change cells for human detection result. The upsampling is done because the IR only provides a native 32 by 24 frame, which would appear very blocky on the display, so increasing it to 64 by 48 with interpolation does not create new thermal detail. It produces a smoother, easier to read heat map on the screen. The thermal scoring logic computes an average ambient temperature across the frame, finds the hottest pixel, counts pixels that are meaningfully hotter than the background and within a plausible human temperature range, and then updates a persistence-based present score. That score rises when enough hot pixels and sufficient peak temperature suggest a human target and fall otherwise, so detection is less sensitive to single frame noise or brief temperature spikes.
Here's an overview of the code that runs on our ESP32. The opening section defines SPI pins, I2C addresses, and a GPIO expander. Separate blocks handle initialization flags, calibration values, and output variables separately for the thermal camera, the IMU, and the radar. A tile-based menu lets users select thermal, radar, INS, or a placeholder scan. Eventually, scan mode will allow us to access each component in order to corroborate human detection readings and contribute to a confidence score. Each tile is defined by a struct that bundles things like position, dimensions, color, target mode, etc. Each mode has its own screen layout with a top bar containing contextual buttons. Rather than centering text algorithmically, each tile specifies an explicit label X and label Y pixel coordinates. This gives us precise control over where the text appears. The radar uses two UART connections, one for sending configuration commands and another data port for receiving TLV framed packets. The parser extracts breath rate, heart rate, and times out detection if packets stop arriving. The ultrasonic sensor measures distance by chiming a trigger echo pulse through the GPIO extender, with results smoothed by a simple exponential filter. Its sole purpose is proximity gating. If the user gets within 25 centimeters, the radar shuts down to avoid near field saturation, and then restarts automatically once they back away. We also have a screensaver feature. After 10 seconds of idle time on the menu, a bitmap image is streamed from program memory to the display. Any touch exits back to the previous screen.
Okay, so we're going to begin this demo with the user interface. So as you can see, we have our screensaver displayed on the LCD screen, and this just appears when the system is idle. So when you tap it, the four options come up, and we have thermal for the infrared sensor, radar, INS, and scan, which runs through all of the systems.
Scan will be interfaced in the